It's science
for the people.
This is Direct Current.
Hello and welcome to Direct Current. I'm your host, Matt Dozier. We're back with the second half of our two-part series on NASA's Mars 2020 mission, featuring the many contributions of the Department of Energy and our national labs to the Mars Perseverance Rover. Last episode, we followed Perseverance's nuclear-powered battery on its journey of nearly 7 years and 5,000 miles to join the rover at Kennedy Space Center. If you missed that, be sure to go back and check it out after you listen to this one. This time, we're looking ahead to the rover's quest once it finally lands on Mars in February 2021. At the top of its to-do list, searching for signs of ancient life and collecting samples that a future mission will one day bring back to Earth. To unlock the secrets of the arid Martian landscape, Perseverance has a lot of tools at its disposal. One of the most versatile is SuperCam, NASA's version of a scientific Swiss Army knife.
SuperCam is really an incredibly capable instrument. It's actually multiple instruments in one really small package.
Nina Lanza is one of the team leads for space and planetary exploration at Los Alamos National Laboratory, where SuperCam was created.
So I'm a scientist. I'm a geologist by training. So I would call myself a planetary scientist because I look at rocks on Mars. And so I am really interested in particular finding biosignatures in rocks. So one of the main goals of the 2020 mission is to collect samples for a future return to Earth, which is so exciting because we've never done that from Mars.
In part one, we talked about how Los Alamos National Lab also played a crucial role in preparing the plutonium-238 fuel for the rover's nuclear heart. And if the power supply is Perseverance's heart, then SuperCam is its eyes, and its ears, and its laser vision? Yes, like its comic book namesake with the blue tights and red cape, one of SuperCam's superpowers is shooting lasers out of its eyes. I'm not even joking, that's really what it does.
We actually take a laser pulse and we focus it down to a spot the size of a pinhead, so very focused laser energy.
Roger Wiens oversaw the development of SuperCam at Los Alamos National Lab. He explains how SuperCam uses laser-induced breakdown spectroscopy to pry information from the rocks by zapping them.
When that happens, there is on a target, on a surface, a small amount of material that is ablated in a very hot state, over 10,000 degrees Kelvin. And that material actually is emitting light. It's very bright. It's like a little ball of plasma or a spark. And by looking at that with a small telescope, a telephoto lens, from some distance away, you can actually tell the elemental composition of the material that you just shot.
Ablated is science speak for zapped, vaporized. Pew, pew.
It's basically burning off a small amount of material, almost basically as atoms, not even as dust, because this material is so hot. And there's a little shock wave that happens when that laser beam hits the surface. It's a very fast pulse of light, and it makes a little zapping sound. We say that we are zapping rocks on Mars, and that is totally true.
It's a really exciting idea. Driving a rover around a distant planet, firing lasers left and right that tell you instantly what things are made of. It's easy to get carried away.
So yeah, when we say we're vaporizing rocks on Mars, people often think really big, and I found a really hilarious picture on Twitter where it looks like an explosion the size of the rover. And it is an explosion, but much smaller.
SuperCam's laser is housed in a shoebox-sized unit atop the rover's mast, nearly 7 feet above the ground. It can fire up to 25 feet away with pinpoint accuracy, feeding images of the laser blast to spectrometers housed in the body of the rover for analysis. It's an incredibly powerful and efficient way to survey a lot of different Mars rocks in a short span of time. How do I know that? Well, because we're already using it on Mars. In fact, we have been for the past 8 years. Enter Curiosity, Perseverance's sibling rover, which landed on Mars in 2012. Remember last episode when we talked about how similar Curiosity and Perseverance are and how much they share in common? This might not come as a total surprise, but Curiosity has laser vision too.
Now, after about 8 years on Mars, ChemCam has shot almost 800,000 laser pulses, each one of them giving us an optical spectrum that gives us a chemistry of these rock and soil targets. And it's a great way to do it because it's pretty fast and efficient relative to actually having to drive up and to sample things for other techniques.
Before SuperCam, there was ChemCam. Roger led the group at Los Alamos that designed and built both instruments in partnership with the Institute for Planetary Science and Astrophysics in Toulouse, France. Both he and Nina are part of the science team that has kept ChemCam running consistently for the better part of the past decade.
I haven't been able to focus all of my attention on 2020 because we actually have another instrument that's on Mars right now, so we still have to take care of our first baby, ChemCam is fully operational. We are operating 5 days a week, actually really 7 days a week, but we don't have to work on the weekends.
ChemCam has been a rock star for NASA, but don't think for a moment that makes SuperCam any less impressive. In fact, the Los Alamos team has managed to cram even more features into the already overstuffed bundle of technology.
SuperCam is almost exactly the same size as ChemCam is. We were able to fit these new techniques in pretty much without adding mass or weight to the instrument. Both ChemCam and SuperCam weigh a little over 20 pounds, just a little over 11 kilograms actually. And so that's pretty lightweight for doing all of these different things. We're pretty proud of that.
So how is SuperCam going to outdo its older sibling? Let's unfold the Swiss Army knife and see what sort of gadgets it has in store. First of all, the laser got a fancy new upgrade.
We actually have a new capability, which is also laser-based, that's called Raman spectroscopy, which doesn't vaporize rocks, but it does tell us the mineralogy, the structure. And so for geologists, this is amazing because what do we want to know to be able to identify a rock? Well, we want to know the chemistry, what's in it, and the mineralogy. How are those elements arranged?
Then there's the remote microimager, essentially a camera that lets scientists see precisely what they're targeting with the laser, down to individual grains of rock or sand.
We're also expanding the range of our spectrometers so we can use them in a passive way. So we're not just collecting the light from our laser analyses, but we can just open up the spectrometers and look at reflectance spectra. So that's a very traditional technique for understanding mineralogy and rock type.
But wait, there's more.
Last but not least, we are putting a microphone on this instrument. And so it sounds crazy, right? Everyone's like, why are you doing that? Well, it's not just to hear what the Martians are saying about us behind our back. It's also to hear the sound when you shoot the laser in an atmosphere. When it hits the target, it makes a snapping sound.
Maybe you had the same reaction. What's a microphone doing on a rock-zapping laser? For the SuperCam team, sound actually adds another dimension to what they can learn about the makeup of a rock with each shot of the laser.
And so by listening to the sound of those zaps, we can find out, without touching the rock, how hard it is. And so those three kind of qualities, or four kind of qualities, the structure or texture of the rock, the chemistry, the mineralogy, and its hardness, those really define a rock very well in many different ways.
That extra dimension has big implications for some new avenues of research.
So the thing I'm really excited about that I've been doing some research in is, trying to figure out if a rock has a coating on it just from listening to the sound of the laser zapping. And the reason we care about coatings is because a coating on Earth and on Mars is the result of the rock surface interacting with water, with the atmosphere, and in Earth's case, life. So it's a really cool record of everything the rock has experienced.
And then there's the sheer novelty of being able to listen to the sounds of another planet.
It's the first time that we're going to have a microphone operating on Mars. And so we're really curious what it's going to sound like. Some tests have been done in a low-pressure chamber, and it turns out that the microphone will likely be sensitive to the wind. That's the sound that the microphone will hear, the sound of turbulence when it's windy on Mars.
As if that wasn't enough, the pops of the laser firing have yet another useful side benefit on a planet that's entirely covered by a layer of dust.
On rocks, the laser it produces a shock wave, which is what that sound is, that snapping sound, and that shock wave blows dust away. So we can actually clear off the surface of a rock to see what's underneath that dust layer just by analyzing it. It's something that we actually use all the time on Curiosity. Sometimes another instrument will be like, can you just clear the dust off this a little bit, and then we'll take a picture, or we'll do our analysis without the dust.
And that's part of the Swiss Army knife.
Exactly. It's actually crazy how many things SuperCam can do.
Why go through all this trouble just to tell what some rocks are made of? Well, as I said at the top of the show, a couple of reasons. The main one being our continued hunt for Martian microbial life. For NASA, that search has been guided by the mantra, follow the water. We know that Mars once had lakes, rivers, and possibly even an ocean at some point in time. Curiosity's landing site, Gale Crater, and Jezero Crater, where Perseverance will touch down, are two places where significant bodies of water likely existed in the past.
You know, we learned so much about Mars in Gale Crater, and now we're going to be able to actually test some much more complicated hypotheses in Jezero Crater, which has an environment similar to Gale. So Gale Crater, we know, was host to a lake or a series of lakes that had long-lasting water. Jezero appears to be a very similar type of environment with some important differences. And so I'm really excited to sort of have another place to test ideas about Martian lakes. These two craters are really similar in age. So now we're going to learn more about this time on Mars when water was abundant.
Today, evidence of the planet's watery past, and with it any traces of biology, is now locked in what remains on the dry surface, rocks. So that's where Perseverance is going to look.
When you think about understanding the makeup of a rock and maybe how it was formed or what were the conditions under which it was formed, that's what we're really interested in Mars, because the record of what happened on Mars is now sealed in the rocks. And so we're wanting to understand those rocks.
Currently, the only rocks we have from Mars here on Earth are Martian meteorites, which just so happen to have been Roger's first foray into planetary science.
I was very interested in space from my childhood. I grew up in a rural part of Minnesota and worked on a farm. When I got into graduate school at the University of Minnesota, I was able to work on meteorite samples that are, it turns out, those meteorites actually came from Mars. They were a part of Mars that got chipped off with a very big impact and eventually found their way to Earth.
The meteorites are fascinating, but there's one big problem.
We don't know where on Mars they're from. We don't have a way to tell where on Mars they came from, where they were launched from.
Barbara Cohen is a planetary scientist at NASA Goddard Space Flight Center.
What I do is called Geochronology, and that is the science of saying when a rock formed. And when a rock formed tells us how to put them in order, how to put the pages of history in order. So when we say a rock formed in a volcano, or it formed in a riverbed, or formed through erosion or through accumulation, all of those things are great. We want to know those things. We want to know when they happened on Mars, when were volcanoes on Mars, when was there water on Mars. So we want to put those in order, and we want to say what was happening to the planet in what order. So geochronology is what does that for us.
Why does it matter that we don't know where the meteorites are from? Well, for one thing, it makes it hard to tell how old they really are. Planetary scientists actually have a pretty interesting way of figuring out the age of rocks on other planets. I'll let Barbara explain.
So when you look at a surface and you can count the number of craters, it's like when you have a piece of paper and you put it out in a rainstorm. So you put two pieces of paper out and you take one in after 1 minute and you take one in after 5 minutes. The one that's got more raindrops on it was out for longer, right? That's how it works. Craters work the same way. The longer a surface has been exposed to space, the more craters it accumulates. So we can count the number of craters or the crater density, but until you have a rock from that surface where you can date it and get the absolute age, you just know that something is older or younger. It just has more craters or fewer craters. And for Mars right now, that's all we have. We know places that have more craters. We know places that have fewer craters. So we know some things are older than other things, but we don't have any absolute ages. And the reason for that is we don't have samples that we've picked up from a particular place that we can count the craters on.
Because we don't have any Mars rocks we can match to a certain part of the planet, all we can really do is guess at their ages. So what's a geochronologist to do?
Perseverance is the first step in sample return, which means that it's going to go and collect the samples. It's going to drill the samples and collect them. But then we need another mission that will go pick up the samples, launch them off the surface of Mars, and then return them to the Earth. And that's a pretty involved endeavor.
Sample return is the mission I alluded to at the beginning of the episode. SuperCam is going to play a critical role in zapping Jezero Crater's rocks to help scientists pick out and package the very best samples for a future mission to deliver back home to Earth.
How does the team make these decisions, right? How do we decide what to sample? So part of that is based on what we see, right? We have orbital data, but we don't know what's on the ground. But based on what we know from orbital data, we have established a number of samples that are must get, right? We need to get a sample of a regular igneous rock that's in Jezero crater, our landing site. We need to get, if we can, a piece of carbonate material. We need to get this kind of sedimentary material. There's a whole list of those things.
Choosing those samples carefully is of the utmost importance for Nina and the SuperCam team, since we're talking about sending an entire follow-up NASA mission to Mars and back, just to pick up those little pencil-shaped containers of rock and dirt that Perseverance will leave behind.
So to me, that's the most important part, is picking the samples that you want, picking the samples that are going to be returned to Earth. So that's why I'm very excited about Perseverance. When we get those samples back and we can date them and have that first tie point, it's going to snap the whole rest of the Mars framework of history into place. It's going to be very exciting.
For Nina, there's a lot of things she's looking forward to as Perseverance embarks on its exciting new mission. Working on Mars time is not one of them.
An Earth day is about 24 hours long, but a Mars day is 24 hours and 38 minutes long. It's really close, right? But if you want to start on the same time, at the same time every day on Mars, that's 38 minutes later on Earth. And so you're constantly shifting your cycle and you never start at the same time.
I even had trouble wrapping my head around this. Okay, so you know daylight savings time? Spring forward, fall back, and all that? On the rover's first day on Mars, let's say you set your alarm clock at 7 a.m. here on Earth to correspond with 7 a.m. on Mars. If you want to get up at 7 a.m. Mars time again the following day, you've got to spring forward, 38 minutes instead of the usual hour. So instead of going off at 7 a.m., your alarm clock goes off at 7:38. No big deal, right? Then do that again the next day, and the day after that, and the day after that, springing endlessly forward as your days slide into darkness, then back into the light, and back again, 38 minutes at a time.
When I did that for ChemCam and Curiosity, I actually stopped sleeping, basically. I just couldn't sleep anymore because you can't get on a cycle, at least I couldn't, that wasn't related to what the sun looked like outside of my window, right? Like, some people are great at Mars time. Like, one of our team members, she's like, I was born for Mars time, so she might actually be a Martian. I think I've discovered I'm a terrestrial, so that's hard. That's really hard. That's probably coming again, right? You know, and there's just no way around it. So I think I understand a lot more the challenge that's before us, but I'm no less excited about what we're going to find.
Even with SuperCam nestled inside Perseverance on its way to Mars, there's still plenty left for Roger and his team to do during the ride over.
We're very, very busy right now working on software to control and operate these instruments and get the data back and understand it. And so that work's going to continue on through the cruise to Mars and up to the landing. I think with COVID, we don't know exactly whether we will be still operating from our kitchen tables or if we'll be at Jet Propulsion Laboratory working directly there. But we will have the time as the days tick by to get all of these things tested out and operating on the surface of Mars.
For a few moments, though, all anyone involved in this mission can do is hold their breath.
The launch is always a bit nail-biting. And then when it comes to the landing on Mars, we're not in control. It's all happening remotely without any kind of control from the Earth because of the distance. And we just kind of get the signals before it goes in and hope and pray that it all works. I generally have confidence, but there's a certain emotional side of me that worries, definitely.
There's a measure of faith required in any big scientific undertaking, be it a deep space mission like Perseverance or the countless other projects our national labs tackle that span years and even decades. Massive investments of time, energy, and money hinge on the skill, dedication, and coordination of hundreds of people. The outcome is rarely certain, but the risks are worth taking, and the benefits can exceed our wildest expectations. We'll close, once again, with a look to the future from Secretary Dan Brouillette.
Earlier this year, on behalf of DOE, I had the privilege to join the National Space Council, which is chaired by Vice President Pence. And through this council, we're working to expand our cooperation across the entire government with all of our interagency partners. We're working with NASA to support the Artemis mission, to land the first woman and the next man on the moon by 2024. And then we're going to take the next big leap, which is to Mars. We're also working with our colleagues at the Space Force to protect the nation, and we're working with our colleagues at the Department of Commerce to increase the flow of our best space technology to the market, to the private sector. And that's to ensure that the U.S. is poised to compete well in what we hope will be a $2 trillion future space economy. And whether we're exploring the universe or developing earthbound capabilities, our mission remains absolutely the same. And that's to ensure our country's security and prosperity through the transformative solutions in science and technology. It's something that our people do very, very well. They do it each and every day. And I'm incredibly proud to be a small part of their team.
That's it for our two-part series on NASA's Mars 2020 mission and the Perseverance Rover. It's been quite a ride, so thanks for sticking with us. I'd like to thank everyone who helped out with this episode, especially Roger Weens, Nina Lanza, and all of the fine folks at Los Alamos National Laboratory. You do amazing work. Thanks as well to Barbara Cohen and NASA Goddard Space Flight Center. If you haven't had a chance to listen to part 1 yet, go check it out. You can find that episode and all of our episodes at Energy.gov/podcast. And if you're hungry for more Mars 2020 content, you're going to want to head over to mars.nasa.gov. If you've got a question about this episode or want to leave us some feedback, email us at directcurrent@hq.doe.gov or tweet at Energy. And if you're enjoying the show, share it with a friend and leave us a review on Apple Podcasts. Direct Current is produced by me, Matt Dozier. Sarah Harmon creates original artwork for all of our episodes. This is a production of the U.S. Department of Energy and published from our nation's capital in Washington, D.C. As always, thanks for listening.